Okay, we want to present now a derivation of a function that we used earlier in the course several times. I'm talking about thermometry, infrared thermometry, and also in talking about radiative heat transfer. It's the Planck function. Now, to start with, let's use a couple of ideas from statistical mechanics to motivate a certain result about the probability of a given state being occupied. So we saw in our previous section that probability depended on the multiplicity of that state divided by the total number of states. Now, remembering the statistical definition of entropy, we rewrite that. First of all, we take a ratio of the probability of two different states, and then in terms of their multiplicities, we arrive at this relationship here. So obviously the total number of states cancels out. And so we see the probability is the ratio of the probabilities is the ratio of the multiplicities. Now, using this relationship, we can see that these multiplicities are going to be exponential functions of the entropy of those states. And so we've got here e to the s2 minus s1. Let's just call it e to the delta s over k, the Boltzmann constant. So that's the ratio of the probabilities of these two states based on statistical mechanics. Now we want to relate that entropy of the state to the energy of the state. Remember the first TDS equation. TDS is du plus p dv. Now let's look at a non-gaseous system where this really isn't going to be changing significantly at all. And then let's add up ds. So that'll be adding up 1 over t du plus p over t dv. But we're saying that this term here, this is small, so that's approximately 0. And let's find, so for our system, let's imagine that it's coupled to a thermal reservoir, and that thermal reservoir will stay at constant temperature, so the temperature term can come out here. And so we see that the entropy change of this thermal reservoir just ends up equaling the change in internal energy over whatever that fixed temperature is. But for our system then, its change in internal energy will be opposite to that. So delta S for our system will be minus delta U over T, just simply because energy that flowed into the reservoir came out of the system and vice versa. So if we put that into the previous relationship that we had, which was e to the delta S over K, we could see that that's going to now be e to the minus delta U over KT, or rewriting that in terms of values for the two states. This will be U over KT, and this will be U1 over KT. What is U? It's energy. And then, so we'll just cross multiply that then, and get state 1 and state 2 matched up with their corresponding variables. So P2, cross multiply this one down. So the probability of being in state 2 over that exponential function is the probability of being in state 1 over this exponential function. And if this is true for all macrostates of all sorts of different energies and at all temperatures, in fact, the only way that this can be true is if this thing is actually a constant. And we're just going to define a letter z. We'll say, okay, this constant is 1 over z. So rearranging that result then, we probably find the probability of a state I is some constant times e to the minus u over kt. And that constant we defined as being 1 over z and so this is the probability of state I, so I'm going to use a little subscript here for the energy of state I. And instead of ui, I'm going to use ei for the energy of state I. Okay. And then I'm going to define just a symbol here, the beta symbol, and that's reciprocal kt. And thus, we can write that the probability of state I is 1 over z, that's just a number, times e to the minus beta energy of state I. And this is a very familiar expression in statistical mechanics. Now, it must be, of course, that the total probability of being in a state is 1, because clearly the system must lie somewhere. So if we add up all the probability i's, we get 1. And of course, that's the same as adding up our 1 over z constant, e to the minus beta times energy. So our beta is 1 over kt. And z, of course, is a constant, so it comes out of that summation. And so now we see that really what we're getting here is a definition of this z. So cross-multiplying it up, we see it's the sum of all of these little exponential functions over the energies of all the states. And now it has a name. This is called the partition function. Now it has no units because if you do energy over kt, kt is also an energy, so that gives a dimensionless exponent. So z is just a number. It's adding this all up, and the probability of a given state, let's say probability of state I, is still 1 over z times this exponential function. Now, this is the key fact in statistical mechanics. So the rest of the statistical mechanics course would all be about that. Now notice that if our temperature is fairly low, such that the energy of the state is a lot bigger than kt, then what happens to that, to the system, is with the thermal energy being really low, this is a big number, e to a minus big number is really close to 0. So that state is unoccupied. That state is very unlikely, let's say. So we see that you have to have enough thermal energy. You have to have a thermal energy that's, on the same order of the energy in order for the state to be occupied. So if the thermal energy increases, say it was equal to this, then this would be like e to the minus 1. It would be 1 over e. And so, that would give you some non-zero probability. So as kt gets really, really big, as the system gets really hot, then this goes to 0, and e to the 0 is just 1. And so that would be like the maximum probability of that state being occupied. So we see that for the state to be occupied, the thermal energy must exceed the energy of that state. So now we've got a probability function for the system to be in a given state. And so now we could talk about what the average energy of the system. So this is going to be a sum over all the energies weighted by the probability of that system being in that state. So the probability of being in state I, we saw already, is reciprocal z, e to the minus beta times its energy. And so then we multiply that by the energy, and then we add up over all the states. The z, again, this partition function is a constant, so it comes out. And so we're left with adding up this function over all states. Now, it can be shown, and this will be your task in an assignment, to show that this is actually just a derivative of the partition function. That's a pretty easy thing to show. We'll get you to prove that. Now, we're going to use this fact. And remember, we're trying to prove the Planck radiation law. So this is going to be like the average energy of a certain radiative state. And we need that now. That's a key fact that we're going to need to do our Planck derivation. So let's just park that for now, and then let's go back and start talking about thermal radiation. Let's look at radiation in a box, in a closed cavity. Let's say like a kiln or the oven in your kitchen. Now that cavity is filled with electromagnetic radiation, thermal radiation. A lot of it is in the infrared. Now, that radiation comes from vibrations in the walls of the cavity, and the walls of the cavity, those atoms and molecules are therefore vibrating, and we know from quantum theory that those vibrations have to be quantized. So according to the Planck hypothesis, those energies only come in discrete amounts, and therefore the energy of the thermal radiation only comes in discrete amounts. It's multiples n of hf, where f is some frequency. Okay, so there's the quantization hypothesis for the radiation. Now, we are dealing with waves, electromagnetic waves, and so all traveling waves can be written in this form. And so we want to find the partition function for this electromagnetic radiation inside this cavity. We saw that that partition function is the sum over all states of this exponential term. And for our electromagnetic waves, due to the quantization hypothesis, the energy is nhf. And so the sum over all states I becomes the sum over n from 0 to infinity. So we're adding up this e to the minus beta energy, where the energy is the energy of the vibrations. And so this actually is a geometric series. And so we have a common ratio here of e to the minus beta hf raised to the power n, summed from n is 0 to infinity. And so we can use the familiar geometric series result, that's just a over 1 minus r. So a is identically 1, the first term in the geometric series, and r is the common ratio. It's e to the minus beta hf. Remember that beta is reciprocal kt. And so that'll come out in the final statement of the Planck function. So for our partition function then, it's got to be 1 over 1 minus this expression, e to the minus beta hf. And so then we can find the average energy of an electromagnetic wave at frequency f using this partition function, because as we just stated previously, with the partition function, you can find the energy by doing this derivative with respect to the beta parameter. And so we're going to need to do a little bit of algebra here. First of all, reciprocal z, the reciprocal of this thing, well, there's a minus here in front. And then we take the reciprocal of z. Then we've got to do the derivative. We'll just use the quotient rule. So square the denominator. Derivative has no numerator, so this is just minus numerator times derivative of the denominator. Derivative of the exponential function is itself times the derivative with respect to beta of the exponent. So that's that. Now we've got 4 minuses, which all wipe out. This cancels one of these terms in the denominator, so just one of them survives. And then we've got hf e to the minus beta hf. Now we're just going to multiply top and bottom by an exponential function, because that will just simplify it a little bit. So in the numerator we only have hf, then in the denominator we get e to the beta hf minus 1. So that's the average energy of an electromagnetic wave at frequency f. Now we need to relate that frequency f to the electromagnetic wave, and here's how we're going to do that. We're going to say that in our cavity, which has dimensions L by L, the electromagnetic waves are standing waves. So you take two traveling waves and you add them together, and you'll get a standing wave pattern. Something like this. So this is the spatial part, and then this is the vibrating part. You get this just using a trig identity, adding a traveling wave that's going right to a traveling wave that's going left. And really, this is just a mathematical trigonometric identity. You could show that this plus this will equal this. Now, because the electric field is going to go to 0 in this cavity, let's say it's a conducting wall, then electromagnetic theory tells us that the electric field has to go to 0. That means that we have a standing wave pattern here. Now, I didn't draw it very well, but that was intended to be the third harmonic. And there's a familiar result from Physics 1 that says something about the wavelength of those standing waves. It just is related to the size of the cavity and the harmonic number n. Remember that we're trying to relate frequency to the size of the cavity. And so we want to solve for frequency. It's c over lambda, and reciprocal lambda is n over 2L. So if we look at this spatial part of our traveling wave then, just the x part, k, this k is related to this lambda. It's 2 pi over lambda times x. Okay, so this is the k right here. This is k. And now we'll substitute in the standing wave relation in there. It's 2a cosine pi n over L times x. So that's what the electromagnetic wave would look like in the cavity. But of course, this is like a one-dimensional wave. We would, of course, have a three-dimensional wave. So we'd have a term like this for x, for y, and for z. And so we see that there's three little vibration numbers, three little quantum numbers related to the x, y, and z vibration. So we would define the overall quantum number for that electromagnetic wave as the sum of the square of those, and the overall quantum number of that vibration will be related to the frequency f. Now we're interested in frequencies that are between f and df. That means we need to find n's that give us frequencies in a certain range. Well, this is going to be defined by, you can see there's a bunch of x's, y, and z combinations that will give you a given n. This is really the equation of a sphere in n space. Here's a picture of the sphere, and so all n numbers that lie on this surface will give you the correct magnitude n to get the correct frequency f. So the relation between n and f will just cross multiply and say, hey, the radius of that sphere in n space is given by this expression. And in order to end up between f and df, you have to have a thickness for that sphere. This is then a spherical shell. So this will be the thickness in n space. It's 2L over c df. Now our n values are only positive, okay? But it's going to be easier for us to integrate over the whole sphere, and then we'll just divide it by 8 at the end. Because then we can say, hey, what we've really got here is a volume, right, for this spherical shell that is surface area times thickness. This will be the set of all n values that give us the frequencies that we want in this frequency range. So the surface area will be 4 pi n squared. The thickness will be dn. So that would be the entire sphere. Then we're just going to divide by 8 at the end. Now there's a comment down here at the bottom that justifies that expression. So why do we have the 1/8? Well, it's because we're considering all n values, including the negative ones, to get this easy expression. And then we're just dividing by 8 at the end. Okay, so we're ready now to find our energy. And it just means we've got to add up all of the electromagnetic wave energy between f and df. Now there's a few factors to consider. First of all, the average energy per mode. We had that a few pages back. This came from our partition function. Okay, so that's how much energy is in each mode. Now how many modes are available? Well, those are all the values of n that give us the correct frequency range. And then the last thing is we need to, I guess, know from electromagnetic theory that for a frequency f, there's actually two different electromagnetic waves. It could be polarized clockwise and counterclockwise, or it could be polarized in there's two independent polarization, 2 degrees of freedom there. Okay, so we're going to sum this up. What are we summing over? Well, we're going to sum this over frequencies. And because Planck's constant is really, really, really small, there's infinitesimal separation between these frequencies. This is going to be an integral over all frequencies from 0 to infinity. So this is energy. This is the energy of the electromagnetic wave inside this box, which is L by L. Now, for n squared, we'll substitute from the top of the page there. This will be 4 pi and then n squared. So n squared, what is that? That's going to be another 4 L squared F squared over C squared. And then this dn, that gives us another 2L over C df. So we've got some numbers to straighten out there. But first, we're going to actually pull out this L squared and L. That's L cubed. That's actually the dimensions of the container. So if we pull that out in front and then divide it to the other side, we're going to get energy over the volume of our hot oven. So this is like an energy density. It's an energy per cubic meter. And then that just gets rid of the L's on this side. So in terms of numbers, 8 gets canceled off by 4 and 2, but there's another 4 and 2 that survive. I'm going to leave the 4 with the pi over C. And then the 2 is going to stay here. There is a factor of Planck's constant from there. There's one frequency and then 2 more, so that's frequency cubed. So I kept the C, but there's still a C squared. And you'll see why I'm doing it in this way shortly. This is df, this is e to the beta hf minus 1. Why did I do that? Oh, look, it's Planck's equation emerging naturally. So what do we have? Well, we have that the energy density in a hot cavity, like a hot oven, the energy over volume, so we could use, U or E for energy, and we found that that was add up over all frequencies, this 4 pi over C 2h f cubed over C squared, and then I ran out of room, but it's df. I'm going to have to pause for a second, fix this. So there, I moved that over a little bit. So there it's df over e to the beta hf minus 1. So that's the total energy per unit volume. So the little bit of energy in that volume is given by this expression here, 4 pi over c 2h f cubed over c squared. And so this is just not the total energy, but the little bit of energy in the frequency range df. And now we say, oh, this is exactly the Planck function here. So the little bit of energy per unit volume in the range, frequency range f to df, is given by some number, 4 pi over c, times the Planck function. So we're starting to make progress here, right? We're not quite there yet in terms of the overall Planck function, but we're getting close because it's now finally emerged. In order to get there, of course, we have to let some of the radiation come out, right? We have to consider like a black body, which means the radiation is leaking out and spreading out over space. So here's a little hole then in our cavity, and this is the inside of the oven. And we're going to consider all the radiation here that's about to leave our cavity in the time t. Now that radiation will be a distance capital R away, where that's just speed times time, and it's electromagnetic radiation, so it travels at the speed of light. And then let's consider the radiation bit here coming from an angle theta. Now, not just radius r, but a little bit further, like dr, would also reach that hole in time t, between time t and t plus dt. And so the thickness of this sphere will be dv, or dct, or c dt. Okay, so now, this is the radiation coming from here that's going to hit the hole, but of course, not all the radiation coming from there is going towards the hole. Only a part of it is. So we've got to do some more accounting. Okay, so first of all, that little bit, how much volume is it? Because we need to know how much energy it is. Well, it's r squared times the little bit of, sorry, this is the Jacobian and spherical coordinates, so that's r squared, and this is going to be sine theta, d theta, d theta, d phi, dr. So, whoops, not in red, but in blue. So this is our volume of that little bit. And then dr, the thickness of that sphere, is c dt. And then the rest of this we'll just keep as d omega, a little bit of solid angle. Okay, so as we were saying just a moment ago, not all the radiation is traveling towards the hole, right? It's going to be equally likely to be going in all directions, and that means we need to consider how much solid angle does this hole occupy on this entire sphere of radiation. So it'll be the angle of the hole, how much solid angle you've got there, over the whole solid angle of the sphere. And the solid angle of the hole is going to depend on its area. But of course, it's going to be the projected area, because if this is a little bit of area dA, and if we're looking at observation angle theta, so this is theta, this is 90 minus theta, so this will be theta again, we see from angle theta, the area that we see is only dA cos theta. So that's the amount of area on the sphere, and then the total area of the sphere is 4 pi big R squared. So this ratio gives you the ratio of the solid angles. And so now we could figure out how much energy is going to be reaching that hole. We're going to have to use the energy density. Okay, let's see, is this on the next page? Yes, here it is. Okay, clear all that off. So we're going to take the energy density, and then we're going to multiply by the volume of the small bit, and then the portion that's directed towards the hole. Now we saw that the energy density was 4 pi over c times the Planck function dF. And then the volume of that small bit that's where the radiation is going to reach the hole in time between t and t plus dt was given by this expression here. And then we have to multiply by a ratio. This is the amount that's actually directed towards the hole. And so there's a bunch of cancellation that happens now. And so this is the little bit of energy that's going to flow out of the hole. And so what we get out of that is our Planck function times cos theta, the observation angle, and then times the little bit of frequency, the little bit of solid angle, the little bit of time, and then that little bit of area. So in other words, what is our Planck function? Well, our Planck function is how much energy you see per unit time, right? That's where the unit time, per unit frequency, unit solid angle, and then per bit of surface area, which is exactly what we claimed very early on in the course for our Planck function. And then there's a cos theta term that you apply when you're not looking at near normal incidence. So this is the watts of power, energy over time, per unit frequency, unit solid angle, unit area of surface. And I'll say it's given by the Planck function cos theta if you're looking at observation angle theta. This is what it would be at near normal incidence. This then completes the derivation of the Planck function, and we'll have a look at this function in a bit more detail in class, now that we've finally derived